Next, we're going to look at straightening curved scatter plots. If you're given a curved scatter plot from your data and you want to fit a line to it, it would be inappropriate to do that, because if the scatter plot is curved, there's some underlying process that's causing that curvature, and a linear model would not be appropriate. Now you might ask yourself, why not just fit a curved model to our curved scatter plot and be done with it? Well, all the regression inference that we've learned in this course is based on straight line relationships, best fit lines, using the least squares criterion, and we don't have the inference methods available for curved relationships like quadratics or exponential or other kinds of power relationships. So what we want to do is to transform the data in some way to make the scatter plot straight and then fit a line to the straightened scatter plot. Now there's a good news, bad news scenario here. The bad news is that there is no linear transformation of the x values, the y values, or both that can straighten the curved scatter plot. Linear transformations transform all of the x values or all of the y values uniformly. They will not change the curvature of your scatter plot. However, the good news is that you can straighten a curved scatter plot by applying a nonlinear transformation, either to the x values or to the y values, or perhaps to both. And when you do that, you're generally going to use logarithms to help you to do that job. The most common and convenient nonlinear transformations that we use involve taking logarithms of the data values. Now, there are two major families of models that we're going to look at in this context. And the first big family is the family of exponential models. They have the form y equals a times b to the x power. Here, x, the explanatory variable, is the exponent. That's how exponential models get their name. X is the exponent. A scatter plot of y versus x would be curved if this were the appropriate relationship between x and y. But if you log the y values and plot the logged y values versus x, that scatter plot would be straight, and the best fit line of the form log y equals a plus bx would be an appropriate linear model. And you could do inference on this for, say, your slope coefficient. You want to maybe construct a confidence interval for the true slope, or do a t-test for the involving the true slope. Now, in this situation, I've got little a and little b, lowercase a and b. Up here, I have uppercase a and b, and these are related. And in order to see how the lowercase a and b that you calculated would give you, and the uppercase a and b that we want in our model are related, we start with y equals a times b to the x, and then we log both sides. And then when we have this expression on the right that we could apply our properties of logarithms to. There's a product in there, and there's a power in there, and we could apply our product rule and our power rule to that expression. And when we do, we get log y equals log a plus x times log b. If we rearrange that a little bit, we have log y equals log a plus log b times x, and then you'll see that here the y values are logged, but the x values are not logged. Okay, if you match that equation up with this one, log y equals a plus bx, then you see that little a and the log of capital A match up, and little b and the log of capital B match up. And you can find capital A and capital B by rewriting these equations in exponential form. This equation in exponential form is just capital A equals 10 to the lowercase a power, and capital B is equal to 10 to the lowercase b power. So your calculator will give you lowercase a and b. You can transform back to get capital A and capital B using this transformation, and then you can write the exponential model, and you can plug in values of x to make predictions. The other big family of models are the so-called power law models. These show up in lots of situations in science where perhaps force or energy is involved, or perhaps some kind of geometrical structure is involved, and these power laws are pretty common. They have the form y equals a times x to the b power. Here x, the explanatory variable, is the base of this power expression. A scatter plot of y versus x would be curved if this were the appropriate model relating y to x. But if you log both y and x and make a scatter plot of log y versus log x, that scatter plot should be straight. And a best fit line of the form log y equals a plus b times log x would be an appropriate linear model to fit to that straightened scatter plot. Now again, the calculator will give you a and b when you do a regression of log y versus log x, and then you have to somehow transform back from lowercase a and b to uppercase a and b in the parallel model. And the way you do that is similar to what we just looked at for the exponential model. You start with the basic power law relationship, you log both sides, then you apply your properties of logarithms to that expression on the right, expand it out, you get log y equals log capital A plus capital B times log x, and then you match that equation up with that one. You see lowercase a is equal to the log of capital A, lowercase b is equal to capital B. And then from that you could transform back by rewriting these equations. At least this one, rewrite that in exponential form. Capital A equals 10 to the lowercase a, and capital B is just equal to lowercase b. So what your calculator gives you as lowercase b when you run the regression on your calculator, that would be equal to the exponent in the power law rule right there.